Welcome. Good to see you all here. My name is Heikki Linnakangas. I work for Neon, co-founder of Neon, and today I'm here to talk about serverless Postgres. If anyone is here for the gamification of the conference, there is a code, feature 23. I was asked to announce that, so that is feature 23. Few words about me. So I've been with the Postgres community for a long time. Here's an old picture of me wearing a nice sweater with the Postgres elephant on it. Doesn't fit on me anymore. That's how long ago that picture was taken. But I have been working on various features on Postgres, write-ahead logging, that's like the transaction log or journal in Postgres. Various things around storage, indexing. At some point, people called me the B-tree guy because I spend a lot of time on the B-tree. So I've been working professionally, like full-time, on various Postgres-related things since 2006 for different companies. And now I'm a co-founder of Neon, and that's what I'm here today representing and talking about this endeavor. So what is Neon? It's a startup, it's a company. We founded in 2021. But what we do is we offer Postgres as a service. So if you need a Postgres database, you go to the website, click a few buttons, and you have a Postgres database. So we try to make that as simple and developer-friendly as possible. So that's the place to go. We have some unique features, branching. If you want to have a separate branch of your database for every time you run a pull request, for example, or for testing, all kinds of stuff. It's also what we use for backup and restore, the branching feature. But today I'm going to focus on the serverless aspect of it. So we offer Postgres as a serverless service. And there were some hoops on making that happen. I'm going to go through the tricks we had to do to turn Postgres into a serverless database. But what is serverless anyway? So it's a buzzword. Like people like to talk about serverless, but what exactly is it? First of all, there is always a server. Like everything runs on servers. Whether it's in a rack in a big data center somewhere or it's running in your basement, there is always a server. But the point of serverless is that you kind of make it feel like you don't think about the server anymore. So you treat it as a service that's just kind of always there. Typically, you would have a public URL that you connect to, and that's your service. So you don't think about managing a server with an IP address and port. You think about the service rather than the server. Other features of serverless that people expect is consumption-based pricing. So you don't want to pay for the server to be running. You pay for the service that you're getting. So you only want to pay for when it's running or when there's activity. And you pay for the usage, not for the capacity of your server. Other features that kind of make something feel more serverless, it's a continuum, it's a spectrum you can have. On the other hand, there's servers, traditional, EC2 instances or something. On the other hand, there's serverless, and there's a lot of gray area in between. But these are other typical features that you would expect from a serverless service. There's no stop or start operations. You don't stop a server, you don't start a server, it's just always kind of there. Now, you might have, enable or disable or something like that if you want to temporarily disable your service, but you don't think of it as stopping or starting the server. What you also don't want to do is to choose a size of your server, again, because you kind of don't want to feel that there is a server. So it should be automatically scaling. It should not require a lot of tuning. You should not need to go and do this kind of stuff. So it's important that it's a managed service to some extent. So when people talk about serverless, this is kind of what they expect. You don't want to be choosing a size. You don't want to be doing a lot of tuning on that. And it should just scale down to zero. That's important. Like you want it to scale down to zero if you're not using the service. But then you also want it to scale up, infinitely would be the perfect, but at least some reasonable amount. So about Postgres then, so what is Postgres first of all? It's a database service, or server database management system. built in the 90s, in the 20s. It's becoming more and more popular. Like when I started to work on Postgres, or you would go to people and they would ask, why would I choose Postgres over MySQL? And I kind of don't get that question anymore. It's the default nowadays. So unless people have other reasons, they usually start with Postgres nowadays. There's a lot of other good systems if you have special needs, but what people would like to do as the first thing now is to just start with Postgres, and then if you run into issues, you go somewhere else. But Postgres has a very traditional client-server architecture. Like this is inherited from the 80s and 90s. This was how server software was built. So Postgres manages a local disk. It assumes that it has control of the data directory, and that's where your data is. It manages that. If you touch that data directory, you might screw up stuff. So you let Postgres handle that. And it has a very traditional write-ahead log, also called the transaction log in other systems. File systems call this the file system journal. It's the same idea. Postgres calls it the write-ahead log. So we use that for crash safety. If you crash, you replay the transaction log to get back to where you were. It's also used for replication. So you can do log shipping. You can replicate your database by copying the write-ahead log as it's generated. But this is all not very serverless. Like if you think about serverless, you don't want to be managing a local disk and dealing with those replicas and all of that. So that's not a great fit. But I'm going to explain how we kind of solve that. Another assumption of Postgres is that it runs on a single server. Like it has control of that server. It's not distributed natively. There's a lot of projects doing distributed Postgres as well. And you can manage your own replicas, read-only replicas, for example. A lot of people do that to scale out. But one Postgres instance with its one local disk is designed to run on one server. There's also all kinds of limitations internally in Postgres. Like you can't easily change the size of some data structures internally. So you kind of, when you start the server, you have to choose how much cache you want to give it, how much memory you want to give various things. And that, again, doesn't sound very serverless because we would want it to be auto-tuned. So how did we do this? How do we run Postgres in a serverless fashion? How do we create this illusion that there is no server? It's just a service that is managed automatically. I'm going to kind of spill the beans here. This is how we do it. So we separated the storage and compute. That's for the first two problems. Instead of running it on a single bare metal instance or server, we run it in a VM, which we can then move around and do stuff with. We added another layer of cache to work around some of the limitations. And then there's pooling and an HTTP API. And I'm going to talk about each of these components. A few words about the Neon architecture. By the way, if anyone has any questions at any point, just shout loudly or raise your hand and shout loudly. But in a nutshell, this is what the Neon architecture looks like. There's a few components. What you don't see on this picture is Postgres yet, but I'll come back to that. So there's a proxy, there's a control plane, and there's the storage, and then there's a Kubernetes cluster where we actually run all of the VMs. So when your application makes a connection to the database, what you see as an application developer is just a URL. It's an endpoint name, blah, 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 something, something, .neon.tech. And you type that into your application or your PSQL or whatnot. But what actually happens when you connect that endpoint is that the connection goes first to the proxy that we run. The proxy is a multi-tenant thing. So they use the same proxy for all of the endpoints, or so there's a cluster of those. So the proxy intercepts the connection. It speaks the Postgres protocol, so it understands what database you're connecting to, how the authentication works. So the proxy speaks the Postgres protocol, and the next thing it does, it performs authentication. This is the same authentication handshake if you're using standalone Postgres, but we perform it in the proxy before we even connect you to the Postgres instance. So we perform the authentication from the proxy using the information in the control plane. And after that, that's where the magic starts to happen. So after authentication, that's when we actually launched Postgres. So until now, there was no Postgres running. But when you connect, we spin up the new Postgres instance, and then we redirect the connection to that. And this took a lot of time to make this robust, and there's a few tricks on how we make that fast enough. First of all, like if you think about the traditional Postgres offering or a server, like we need to spin up the Postgres instance very quickly. When we started, we used Kubernetes, and we launched a new Kubernetes pod to run the Postgres, and that took like 4 to 5 seconds. And we got a lot of complaints about that, like that's too slow. When your application is connecting, you don't want to wait 4 seconds to run your first query. So we did a lot of optimization there, and we actually maintain a pool of empty Postgres databases or instances where you just have the binaries and enough information. But all the network stuff has already been set up. And when the connection comes in, we just take the next Postgres VM from the pool, and we tell that VM, OK, you are that database now. And after that, after we have launched the Postgres instance, the proxy forwards the connection to Postgres itself. And after that, the proxy just passes through the bytes. Like it doesn't look at the protocol anymore. It doesn't care what's inside that pipe. It just passes through the bytes to Postgres itself. So that's in a nutshell how we do that. So currently, we can launch Postgres in about 700 milliseconds if we can get the connection from the pool and so forth. So we spend a lot of time on that. And that's a really tight budget. Like we try to launch it in under 1 second. We could probably get it down to 300 milliseconds or something, but that 1 second seems to be enough for people. Like we stopped getting complaints about that. When it was 4 or 5 seconds, we got a lot of people, saying your cold starts are horrible, but we don't get that anymore. Like the people seem to be happy with that. But that like 1 second budget, it's only 1,000 milliseconds. It doesn't give you a lot of room for random network issues for anything, because there's a lot of stuff that needs to happen. First of all, there's the whole handshake with the client itself, and there's a network delay just from the application connecting to the database. You kind of have to reserve 50 to 100 milliseconds just for that, just for doing the round trip to the application and performing the authentication before you even know what they're connecting to. Then we need to perform the authentication, and we need to initialize Postgres, like tell it, OK, you are that database now. Postgres or the VM needs to connect to storage. I'll talk more about that. And fetch the basic stuff like the catalog, so that contain information about the users, what databases exist, and so forth, to get it up and running. It needs to initialize the memory of Postgres. There's a lot of initialization steps there. So altogether, those steps take like half a second, and 700 milliseconds altogether seems to be what we're at the moment. But if you think about that in a traditional Postgres offering or service, like if you click on Start button on a cloud provider, for example, they will not give you a new Postgres instance in 700 milliseconds. It's going to be more like a minute. So this has been quite a challenge for us. Like if starting up the node for us takes more than a second or 5 seconds or so, like we would consider that an outage. Whereas with the traditional non-serverless providers, that would be just normal. Like you wouldn't be expecting that. So a few words about the storage. I mentioned that so the storage is a big part of what makes this work. So we've separated compute from storage. Normally, Postgres manages its local disk. Well, local, it could be a remote EBS volume or something. But from Postgres' point of view, it owns the disk. But we've separated that into what we call the Neon storage system. So this is a separate service we run, and this is behind. It's a multi-tenant service that's behind all of the Postgres instances that we run. We wrote it from scratch in Rust. And it has a lot of cool features like copy on write branching. That's what makes that feature possible. We use Amazon S3, like cloud storage, object storage, to back all of the data. So we actually kind of only consider the storage layer, the servers that we run, as a cache over the cloud storage. So this replaces your traditional backups and write-ahead log archive that you would typically use in Postgres because we keep all of the history. So we take the WAL stream from Postgres and we keep all of that data. But we kind of process it into a different format so we can quickly access any page that the Postgres needs from that archive. But that also makes it possible to do stuff like, create branches. You can create the branch not just from now, but you can create the branch at any point in time. So that's what makes this branching feature replace traditional backups for us. So if you accidentally drop a table, you can go back in time, choose the point in time just before that happened, create the branch there, and you can see the data as it was at that point. This is also what enables us to do read replicas without duplicating the data. So traditionally in Postgres, if you have a standalone primary that's running, and you can create as many read replicas as you want, but you actually need to duplicate all of the data. And again, that can take a while. Like if you have a terabyte database, it takes a while just to copy over a terabyte of data. Maybe you can use snapshots, like file system level snapshots or something to speed it up, but it's a bit of an ordeal in any case. But what we can do with the storage system is that because you can request the data as it was at any point in time. This also allows the read replicas to connect to the same storage. So you can have as many read replicas as you want, reading the data from the same storage without having to duplicate the data. We haven't automated that process, so it's a manual process if you want to create a read replica. But that is probably something that we will also work in the future, so you could have a scale out automatically with read replicas for read-only workloads. So from a Postgres point of view, the Neon storage system just replaces the local disk. You have to make some changes to Postgres to make that work, but it's a small patch. We hook in at a pretty low level, like right where Postgres would normally read a page from disk. Instead of reading the 8 kilobytes from a specific offset in a file on disk, we hooked into that so that it sends a request to the storage system. Get page number, something at this point in time. So from Postgres' point of view, this is pretty non-invasive. And because we work at a low level, it means that all of the normal Postgres index types work, all of the gin index, gist index, if you want to use PostGIS, pgvector, whatever, all of those things work because they operate at a higher level, and we're at the bottom. But what makes this important for the serverless part, and that's really the topic today, is that by having this separate storage system that can replay or return the data at any point in time, this eliminates the delay at startup. So normally when Postgres starts up, unless it was shut down cleanly, you have to start from the last checkpoint and replay the logs to do crash recovery. And that can take a while. Like if you have a lot of data, if you have a lot of updates going on, it can take minutes to do the WAL replay, or even longer. But thanks to the storage system, we eliminate that. So when Postgres starts up, it can just connect to the storage system and start running queries immediately without having to wait for the WAL replay. So this was a critical component in making serverless happen. And that was really needed to be able to do that. So another part, like that's how we start up Postgres in under a second. That's the story behind that. But there's more to being able to call us serverless. And one part is this auto-scaling thing. You can scale down to 0. I showed you how that works. But how do you scale up? Like once you have the service running, how do we add more resources to it? Like if your workload grows or shrinks, how do we do that? So we run Postgres in VMs in Kubernetes, and Kubernetes does a lot of the orchestration and scheduling for us, so that makes it convenient. But there's a little bit more to that. So we run Postgres in VMs, and big part of that is that when you run it in a VM, you can limit the amount of resources that you give it. I mean, Kubernetes can do that with control groups and stuff, but VM gives you better isolation and even more control of that. So what we can do, we can hot plug CPUs and memory into that VM. So if we decide that, hey, this database is running really hot, it needs more resources, we kind of hot plug new CPUs or memory to the VM. So to make that work, I mean, we run on big bare metal instances, all of this. So you share the host between a lot of VMs. And chances are there's usually space in the host. And there's always new databases shutting down and stopping because we shut them down after 5 minutes of activity and we just start up again. There's a constant flux of new databases starting up and stopping. So we can arrange it so that there is always enough space or enough capacity in the host by just moving things around and by the way we schedule them. But we did need to do something with Kubernetes. We actually had to fork the Kubernetes scheduler to know about this autoscaling. Like Kubernetes doesn't have the concept of a pod growing or shrinking on the fly. So that we need to teach it about that. So we wrote our own little fork of the Kubernetes scheduler that understands what is the current size of a VM, how much capacity there is in the host, and makes the decision whether it's okay to grow or shrink it. The VMs is actually also very important from a security point of view. Like Kubernetes pods are not really a security barrier. So we rely heavily, or like the security of the system depends on the VM isolation as well. Postgres has a lot of good security features. You can create roles, you can do role security, databases, grant, revoke, all of that works. But that's all good stuff, but it doesn't really, our threat model is a little different. Our threat model is that because we are running different databases, different Postgres instances that belong to different customers and they must not be able to see each other, we don't rely on Postgres' security features. We treat everything that runs in the VM as untrusted and tainted, and we don't trust any of the stuff that runs inside. So as far as we're concerned, I mean, we can just give people super user access and let them go loose on the VM, and that's also important so that we can run whatever extensions people want to run. If you run your own extension in C, it can do whatever on the system. So there's one. Hot plugging CPUs is kind of an easy problem. Like if the database is running hot and it's using a lot of CPU, it's kind of easy to detect that, and you just plug more CPUs into it. And it's also easy to take away CPUs. Like if they're unused, you can just unplug them from the VM. But what is more challenging is memory. Like how do you actually? I mean, it's easy to add more memory to the VM again, but when should you do that? That's a tricky question. We don't have a great answer for this, but there are a few possible answers to this. So first of all, you could imagine adding more memory if you run out. Like if you actually get an out-of-memory error in Postgres, Postgres can handle that. It'll, if you manage to run a query that uses gigabytes and gigabytes of memory and the server doesn't have that, you will get an out-of-memory error. It will roll back your transaction and handle that gracefully. So that's one idea. Like we could, and we did. We hooked into that. So if you are about to run out of memory, we add more so that you don't run out of memory up to a limit. But that's not actually a very good answer. Like there's a database management system uses memory for a lot of things, most notably caching. Like the big part of most of your memory really goes into the buffer cache in your database. So now the question becomes, the database will probably run fine with a small amount of buffer cache, but it will just be doing a lot of I/O instead. And especially for us, I/O is actually pretty expensive because you are going to the remote storage system, so the caching is really important for us. So what would be the right answer? How do you even detect that your queries would benefit from having more cache? That's a problem we haven't solved yet, but we plan to work on that. There are cache eviction algorithms that can kind of detect that, or you can get hints of that, but we haven't implemented that stuff yet. And the C is even more like harder problem. Like, forget about the caching, but there's a lot of different plans you could get for a query. Like if you do a large join, for example, the planner can choose to do a merge join, it can choose to do a nested loop join, or it can choose to do a hash join. But hash join is only really possible, or it only makes sense if you have memory, enough memory to run that, like create the hash table and do the hash. So the planner knows like the settings to tell it how much memory you have available for that. So that's the workmem setting in Postgres. And that's a difficult one. Like, how would we know if your query would benefit from having a larger workmem setting, and then it would choose a different plan which uses that memory? And that's another problem we haven't solved. You can just crank up the workmem setting, and then your queries will try to use more memory, and that will probably trigger the autoscaling, because when you then actually try to run it, you might otherwise run out of memory. So that's one way to do it. But these are interesting problems. If there's any researchers out there who would be interested to like write the algorithms for this stuff, I think this would be a good research project for someone. So the final part is about connection management. So a connection in Postgres is pretty heavyweight. So when you connect to Postgres, we fork a new process. So it's a multi-process architecture, which is not very common nowadays, but that's how Postgres works. So every time you connect, we launch a new process. It attaches to the shared memory. There's a lot of shared caches and all kinds of stuff. So that's actually starting a new connection is actually pretty slow in Postgres. I mean, this is a common problem. Anyone running big Postgres applications knows and runs into this and then knows about it. So you pretty much want or need to have a connection pooler in front of Postgres to make that scale. Not necessarily. Depends on the application, but typically. You can set, the default max connections is 100. You can raise it up to a few thousand if you're, depending on what you're actually doing with the connections, but you easily start to get other problems if you do that. So yeah, you really need a connection pooler. We run PG Bouncer on each of the VMs, like it's specific to each Postgres instance. We started without this, like when we launched or like very early preview versions, we still have invite codes and stuff, we didn't do this. And this was one of the first complaints we got. Like people immediately started to run into, hey, I ran out of connections, what do I do? Like this isn't very serverless. What we did, we installed PG Bouncer like most people do with Postgres. So a connection has a lot of state. A connection in Postgres there's a lot of per connection caches. There's the relation cache. There's the plan cache for queries that you run. There's a lot of other catalog caches. There's just a lot of per connection caches. And each of them actually consume quite a lot of memory. So even if you could set max connections to 1,000 or something, you probably wouldn't want to do that for performance reasons. Another important state that the connection has is the prepared statements. Like if you're using JDBC or some driver, they will probably do this behind the scenes for you. Or you can do it explicitly with the prepare command in Postgres. You can prepare a statement, and it does the planning at that time, and then you can run the queries by just changing the query parameters faster. But that's also per connection. Like when you prepare a statement, it's attached to that connection. When you disconnect, it goes away. There's other stuff. There's cursors. Like if you run a query, you can declare a cursor out of that, and you can have multiple of those running at the same time. You can fetch from one and then the other, stuff like that. If you're doing large batch processing, that's a common model to do that. There's also a bunch of per connection settings. Like you can change a lot of the settings with the set command, and that is attached to the connection. So all the queries after that will use the settings that you changed. And then there's the stuff like the role that you connected as. what I'm kind of getting at with all of this is that these are all problems when you try to pool the connections. Like if you change a setting in a connection, and then it goes to the connection pool, and another connection, as far as the application is concerned, tries to use that or reuse the connection, it will have the settings already set. So it doesn't like, you can get confused very quickly if you do this kind of stuff. Again, problem for anyone using PG Barnes and so forth. But what I found interesting, or this really clicked to me a while ago, is that this doesn't actually matter in practice too much. Because if you're writing a serverless application, you wouldn't be doing any of those things. Like with the problematic things like cursors, your serverless application is not using cursors. That's the model from the 90s. People don't write applications like that anymore. Or if you do, I mean, you still can, and then you use a direct connection, and it works. But if you're talking about serverless applications, deployed on some developer platform, JavaScript application, something, you wouldn't be doing that. Same with the per connection settings. Like you wouldn't be fiddling with the per connection settings, because as far as your application is concerned, you don't really think about the connection at all. You kind of treat each query as a one-off query that you run. You don't think about establishing a connection and doing stuff on it. So this actually works pretty nicely in practice. That reminds me of one thing. There's another concept related to serverless, which is stateless. If you're writing a serverless application, you would probably also want to make it stateless, and that's kind of goes hand in hand. But the database, it's kind of an oxymoron to have a stateless database, because the whole point of having a database is that it manages all of the states. Like you have gigabytes and gigabytes of states in the database, and you're mutating, you're changing it all the time. So that's like the reason why the separation of storage and compute made a big difference for us. Like now you can have your state moved down the stack to the storage layer, and you manage it there. But your Postgres is, fairly stateless. There's still a lot of internal state, but most of the hardcore state, which is your user data, is down in the storage layer. Finally, once we did all of this, we still got people asking for, can't you just have an HTTP API to run your queries? Like, I don't want to deal with all of this connection stuff, and I have a JavaScript application, and I just want to, make an HTTP request, run a query with the SQL query, and get the result back in JSON. So we actually did that. Like that was a common request. So we actually did implement that in the proxy. If you go to the Neon website, I think there's documentation somewhere on the syntax, and there's some example JavaScript code to do that. So if you don't want to deal with the connections, you can just use the HTTP API to run queries. That's all I had prepared. Is there any questions?